to chapter 5-ish, 6-ish, I think. So we're going to talk about in these chapters or parts of these chapters. We're going to talk about balancing equations. We're also going to talk about different types of reactions and different ways to classify those reactions. So let us get into it here. So obviously a chemical reaction is a result of a chemical change that occurs, and a chemical change that occurs means that what we start with and what we end with is fundamentally a couple of different things, or something new has been created as a result of that. That is basically a chemical change, which is a chemical reaction. We basically represent chemical reactions by using chemical equations. And in a chemical equation, on the left-hand side of the arrow, again, are our reactants. Those are our starting materials. They go to the right-hand side, which is our products, which are our stuff that is obviously made or produced as a result of this reaction. Other things that we commonly do see in equations, we oftentimes will see the states of everybody. So we have S for solid, L for liquid, G for gas, and very commonly AQ for an aqueous sort of substance. A reminder that there is a difference between liquid and aqueous. If it is a liquid, it is a pure substance. So it's really a pure substance by itself. For example, if you had water, that would be just a liquid. A aqueous is typically a solution, and a solution is really made of two parts. It is made up of a part where you basically dissolve it, a solute in a solvent. So for example, if we took water and we took some solid sodium chloride and we dissolve the sodium chloride into the water, which it will dissolve, will give us a sodium chloride solution that would get the aqueous symbol next to it. So liquid is, again, just really one substance by itself, nothing else in there. And something that is aqueous is typically made by, again, mixing a solute, which is a small part of the solution, with the solvent, which is the larger part of the solution. When we look at the arrow as well, there's a couple other things that sometimes will appear on the arrow. Sometimes catalysts will appear up on the arrow. So maybe you'll see something like a metal. Maybe you'll see something like H+, which is representative of an acid being used as a catalyst. A catalyst is not a reactant. It's not a product. And it does not get used up in the reaction. So basically, the catalyst is there to, in most cases, speed up the reaction. So that is basically the purpose of the catalyst, is to usually speed up a chemical reaction, make it occur faster than it normally would, with it not itself being consumed in the process. A catalyst, as you'll talk about if you go 200B, can be just something like a solid, like a piece of metal. And it basically facilitates everybody kind of coming to a specific location instead of just flying around trying to find each other. They all kind of end up at the same point, which allows them to react a lot quicker. It could also be, again, something like an acid, which creates sort of the right environment in terms of something like pH, which allows everything to sort of react a little bit faster and better. When we look at the equation, thank you. When we look at the equation, we do, for example, this guy here, which is H2 plus O2 makes some water. We can look at the coefficients in front of the equations and look at them as a couple of different ways. We could say, for example, there are 2 molecules of H2 react with 1 molecule of O2, gives us 2 molecules of water. The one that we'll use sort of in the next sort of chapter that we get into was the mole to mole relationship. We could say there are 2 moles of H2 react with 1 mole of O2, and that produces 2 moles of H2O. So in a balanced equation, the coefficients are actually really important in terms of the stoichiometry and the relationship between reactants and products, and really the proportion at which they react together to produce a certain amount of the product that will be made there. We'll talk more about stoichiometry obviously later, but again, it's really nothing more than just the actual coefficient that we see in the balance equation. Any questions on any of that there? All right. And again, we see the relationships, and for the most part, when we get into sort of calculations, that is going to be the relationship. This bottom one is conservation of mass. So one of the principles, obviously, is we do not sort of create nor destroy anything along the way in a chemical reaction. Really, the only thing that happens is we pretty much break all the bonds on the reactant side, and they reform on the product side into new compounds. And because we're just breaking electrons, we never ever change anything in the nucleus, like the protons, which are important for what elements we have. That is why we always will need a balanced equation. And that's because when we start with, say, 1 magnesium or 2 magnesiums here, we should end up with 2 magnesiums at the end. We started with 4 carbons on the left, we should end up with 4 carbons on the right. So, you know, they may be in different substances, but we do have the conservation of elements. And that means that, you know, if we had 4 carbons on the left, they have a certain mass at 12 grams each, and they would have the same mass on the other side of like 1201 grams. So there's that conservation of those elements. The one thing we do not use those coefficients for is how many grams of each of those. So that is definitely something we don't do. That's the only relationship that would be incorrect. So let's talk a little bit about balancing equations. And really people, I would say for the most part, do sort of a trial and error. But there is a couple of important rules when you are all done balancing the equation. So let's talk a little bit about those important rules. I'll back it up here. First off, when we do balance an equation, which you always want to make sure that if you are doing something with an equation, it is balanced. The only thing we change are the coefficients. So that is the only things that you can change, which are these numbers that obviously come in front. We never change the subscript, because if we change the subscripts, what did we just do? We basically changed what that is to probably something that doesn't exist. So we never changed any of the subscript. The other popular thing I like what people do is like throw a big number in between. We don't do those either. So it's always the number that comes in front of the formula, nothing else. We want to change coefficients until we get really the same number of elements on each side. So obviously we want the same number of elements on each side. Now, there are really 2 rules that you want to follow when you balance an equation, or you feel like you balance the equation, is all the coefficients, when it's all said and done, do need to be whole numbers. So all the coefficients has to be whole numbers. The other rule is they actually need to be the simplest set of whole numbers. So you got to have basically the simplest set of whole numbers. So for example, if we balance an equation like A2A plus 4B makes 6C, and just say all that's balanced. When we look at all these coefficients, although it may be balanced, we could definitely go through and reduce everybody down by 2 and still get whole numbers. And that is what you should do. So the property balance equation in this case would look something like this, where we reduce those down. So, and that sometimes can happen because people can maybe sometimes see larger numbers to balance it. And you obviously can balance an equation with multiple sets of numbers. But if you can reduce down all the coefficients and still hit a whole number on everybody, then you should do it. And that would be the property balance equation. If you leave it sort of with the higher numbers, it technically is not properly balanced in terms of the equation. What do we start with? What should you do? Frankly, for me personally, I make a table of all the elements that are present, and it kind of guides you as to what to start with. I personally think you should start with what looks like the easiest to balance. That's not in a lot of individual sort of formulas. So you got an element maybe just in one formula on each side. That's a good place to start. You got elements, the same element in multiple formulas on each side, then you might want to save those for the end. A lot of times those things will sort of fall into place as you do it. Some people say start with the more complicated. I don't know. People just throw up some trial and error type of thing. So let's take a look if we were going to balance this guy here. Obviously, first off, it's really important if you're given something just in words that you do write the correct formulas down first. Otherwise, it's going to be a really long night trying to balance it. So you definitely want to make sure that you start with the correct formulas. You also want to, and again, it may not make sense what I'm going to say, but maybe it will. You do not want to ever try to predict formulas and balance at the same time. So people try to do that. And it very much happens a lot of times when you're just given the reactants and maybe you got to predict what's on the product side. And people try to kind of write the chemical formulas and balance it at the same time. Never a good idea. You will end up with probably the wrong formulas. The order in which you want to do that is forget about the balancing part. Just lay down the correct formulas first and then go back and balance it with the coefficients, and you'll be in pretty good shape. So if we're going to do this here, and I'll rewrite it here, maybe C2H6 plus O2, CO2 plus some water. So if I was going to do this, I would personally lay up a table here. I'll have a reactant side, a product side, and just lay in my guys. So I got a carbon, I got a hydrogen and oxygen. On the left-hand side here, we have 2 carbons. Right-hand side, we got 1 carbon. Left-hand side, we have 6 hydrogens. Right-hand side, we have 2 hydrogens. Left-hand side, we have 2 oxygens. And on the right-hand side, we have 2 oxygens there, plus 1 more there. So that would be 3 oxygens in this case. So I have a nice little table that kind of helped me decide maybe where to begin. And again, you don't have to like start with the most complicated. To me, I would think carbon should be pretty easy to balance. So we could lay in a 2 in front of the carbon on the right, again, changing the coefficient. When we do that, that gives us 2 carbons. Hydrogen is still 2. And now in terms of our oxygen, we have 4 here, again, plus 1 more here, which gives us 5. At this point, we have balanced the carbon, so might as well go for the next easiest thing. And this is a situation like I was talking about. If we look at oxygen, we have oxygen by itself on the left, and then it's in a couple of things on the right, which gets a little tricky since it's in a couple of things on the right. But hydrogen's kind of by itself on the left and by itself on the right, only in one thing. That's probably the best place to start next with. And we can very easily fix our hydrogen by putting a 3 here in front of the hydrogen. That gives us, again, for carbon 2. 3 times 2 there is 6 for our hydrogen. And now in terms of oxygen, we got 2 times 2, which is 4. And we also got to distribute that 3 to the back end there. And that gives us 3 times 1, which is 3, which means now we have 7 oxygens at that point. Any questions up to there? So at this point, we obviously have filled in some numbers. On the right-hand side here, we definitely don't want to change those numbers. Otherwise, we're going to be in some trouble. So really, we need to fix the oxygen by coming back over here and trying to fix it. In this case, we need 7. We have 2. We need to turn basically a 2 into a 7. The one way you could do that is you could actually use a fraction to do that. So you could do something like 7 over 2. Because when I take 7 over 2 times 2, the 2's cancel, gives me 7. That means here I got 2 carbons, 6 hydrogens, and 7 oxygens at this point. Can I leave it like this? So I cannot leave it like that because we got to have all whole numbers. So this is a good example that you definitely could use a fraction to balance an equation. And it oftentimes happens like this when you have like a diatomic element on one side and that element and a couple of things on the other side. But you do need to get rid of the fraction. So to get rid of a fraction, we do need to multiply by the denominator, right, all the way across. So we're going to multiply everybody here by 2. And that will get us 2 of the C2H6 plus 7 of the O2, 4 of the CO2, and 6 of the H2O. And if I didn't screw this up, it should obviously still be balanced here. So if we take a look at it on the left-hand side, we got 4 carbons. We have 12 hydrogens and 14 oxygens. Right-hand side, we got 4 carbons. We got 6 times 2, which is 12. And we have 8 oxygens there. And we have 6 oxygens there, which, gosh, I hope is 14. And we are balanced at that point. So you definitely could use a fraction to balance it, but you do have to clear it when it's all said and done. By the way, the simple rule for the fraction is pretty much the top number is the number you need, and the bottom number should match. Yeah, so that's a pretty easy way to figure out the fraction that you should use. Any questions on that balancing there? All right, so let us try a few here just to make sure. Bless you. All right, so balance up that one there, see what you come up with here. Okay, let's take a look at this one. So again, if we make a little table, reactants, products, we got nitrogen, oxygen, hydrogen. Left-hand side, we have 1 nitrogen. Right-hand side, we got 2. Left-hand side, 1 oxygen, 1 on the right, and 2 hydrogens and 2 hydrogens on the right. So clear in this case, nitrogen would be a good place to start. We're going to lay up a 2 again in front, and that's going to get us 2 nitrogens. We now have 2 oxygens and 2 hydrogens. So very common when you're balancing an equation, you fix one thing, but kind of screw up the other things. So again, we just look at our table, and probably the easiest thing to go after at this point would be our oxygen, since that's the only thing that's not balanced. So to fix the oxygen on the right-hand side, we would lay a 2 up in front, and that's going to give us 2 nitrogens, 2 oxygens, again, distributing to both numbers. And that would give us 4 hydrogens there. At this point, we could easily fix our hydrogen by coming back to the left-hand side and throwing a 2 down, and that would get us 2 nitrogens, 2 oxygens, and again, distributing it over would get us 4 hydrogens in that case. Any questions on that one there? Yeah. So a couple more here. All right, let's balance that one up there. Okay, so let's take a look here, see how we're doing. So once again, if we make our table, left-hand side, 3 carbons, right-hand side, 1, left-hand side, 8 hydrogens, right-hand side, 2, and 2 oxygens on the left. Once again, here we got 2 oxygens there and 1 more over there, which does give us 3. In this case, again, the carbon here should be pretty easy to balance. So that's where I'm going to start. I'm going to put a 3 in front of it. That is going to give me 3 carbons. Still 2 hydrogens. Oxygens, I now have 6 from there. And again, 1 more over there gets me to 7 at this point. At this point, the hydrogen, once again, because it's really only in one thing on each side, is probably the easiest to go to next. And we could do that for the 4 there. And at that point, we then would have 3 carbons, 8 hydrogens. Oxygens, we got 6 here, and again 4 here, which will give us 10. That makes it pretty simple now to go back to the other side there and lay up a 5, and that would give us 3 carbons, 8, and 5 times 2 would be 10 in this case. Yeah. Any questions on that there? All right. Couple more here just to make sure. All right, balance this guy up. Okay, so again, making our table here, we got 2 borons on the left, 1 on the right. We got 4 oxygens on the left, 1, 3 there, and 1 there. On the right, we do need to distribute this 3 into both of them there. So we would have 3 oxygens on the right. Left-hand side, we got 2 hydrogens. Once again, distributing that 3 in will give us 3 of the hydrogens as well. At this point, not much to work with, so might have to start with the boron, and we will lay a 2 up in front of it. That will give us 2 for the boron. In terms of the oxygen, in addition to multiplying this guy in, we then need to multiply it out by the coefficient, which means that is 6 for the oxygens, and we'll get the same 6 for the hydrogen by kind of multiplying in and then multiplying out to the coefficient, or the opposite way around, go in and then out to whatever way you go. At this point, clearly you don't want to touch anything on the right-hand side, so we'll concentrate here on the left-hand side. Once again, I'm going to go with hydrogen because it is in only one spot on the left there instead of oxygens in multiple spots. So to fix the hydrogen by going to the left, I could simply just put a 3 in front of it. That gives me 2 boron. It does give me, in terms of oxygen, 3 here, distributing that there. Also takes care of my oxygen, and that takes care of the hydrogen as well. So that will take care of everybody by sort of doing that. And if you are balancing an equation, that's sort of what should happen. At some point, everything should fall into place. If you're there forever trying to balance an equation, then something's probably wrong. Maybe look at a formula or something like that. Or I guess you're just picking the wrong numbers as opposed to the other option. That could happen. Any questions on that one there? All right, here. All right, so give this one a go here. Take a look. So on the left-hand side, we have 1 nitrogen and 1 nitrogen. Left-hand side, 3 hydrogens and 2. Left-hand side, 2 oxygens. And once again, we do have 2 oxygens on the right-hand side, 1 in each of those guys. So really, it is just the hydrogen here that's not so balanced. So we got 3 on one side and 2 on the other. So common number there would be to get to 6. So to get my hydrogen to 6 on this side, I need a 3. And to get my hydrogen to 6 on that side, I would need a 2. That's going to give me 2 nitrogens, 6 hydrogens, and 2 oxygens. Right-hand side going to give me 1 nitrogen, 6 hydrogens, and my oxygens 3 there, and 3 there, and 1 more there makes 4. At this point, the next easiest thing, since oxygen's on a bunch of things, would be the nitrogen. And I can balance that by putting a 2 here. When I do that, that gives me 2 nitrogens, still the 6 hydrogens. Oxygen, I got 2 there and 3 more there, which now gives me 5 in terms of my oxygen. At this point, I want to basically go to the left-hand side. My only option there is the oxygen. And this, again, would be a place where a fraction would be good. We will go with the number we need up on top, which is 5, and we'll match that number there on the bottom, which would give us 5/2. That gives me 2 nitrogens, 6 hydrogens, and 5/2 times 2 is 5 in this case. Again, technically speaking, we are balanced, but we do need to get rid of the fractions. So what we're going to do once again is multiply the entire thing by that denominator. That would give us 4NH3 plus 5O2, 4NO, and 6H2O. And that should give us our properly balanced equation here. We have 4 nitrogens on the left and 4 on the right. We have 4 times 3, which is 12 hydrogens on the left, and 6 times 2 is 12 on the right. Oxygen, 5 times 2 is 10. And here we have 4, and we got 6 more on that side, which would be 10 as well. Any questions on balancing equations? So if we look at just one last thing about balancing, say we have a couple of these sort of equations here. And a lot of times, if you do have an equations that actually have some polyatomic ions in it, it might not be so to your advantage to kind of go element by element, because there's a lot of like distributing in and distributing out type of things that happen with the polyatomic ions. So a lot of times when you do have polyatomic ions, it's actually a good idea just to sort of keep them together and balance them sort of as polyatomic ion units on each side. So for example, if we look, we definitely have phosphate, and we also have phosphate here. We got carbonate, and we got carbonate over here. So if I were to sort of approach the balancing of this, once I sort of see those polyatomic ions, that's pretty much where I'm going to start. So I'm going to start with the phosphate on the left. There are two of them. There's only one over here. That means to fix it, I would put a 2 in front of my phosphate over here on the right-hand side. When I do that, that automatically also changes my sodium, and it also tells me where I probably should go next. So now I have 6 sodiums on the right, and to fix it to get 6 sodiums on the left, I would then come over to the sodium on the left and put a 3 in front of it. That gives me my 6 sodiums I need. That also immediately changes my carbonate, which is on the back end of that, to 3 carbonates. And again, that tells you pretty much where you should go next. I'm then going to go to carbonate on the other side and put a 3. And at that point, gives me 3 irons, which is actually what I need, and 3 carbonates. And now I'm balanced. So a lot of times it's a lot easier to keep the polyatomic ions together, balance them as whole units. And what will happen is it will eventually sort of fall into place. So why don't you take a second here and do the second one and see what you come up with. Let's take a look. So once again, I see sulfate here. I see sulfate here. I do see hydroxide and hydroxide. So in this case, I'm just going to kind of start with the sulfate. So I got 1 sulfate on the left, 3 on the right. So I'm going to put a 3 over here. That then will give me the 3 sulfates that I need. That also now gives me 6 silver, which is where I should go next, to the right-hand side and put my 6 silver. That then also gives me now 6 of the hydroxide. So to get my hydroxide on the left-hand side to 6, I would need a 2. And that is good because I do need a 2 for the chromium as well. And I would be balanced. Any questions on that? Now, if you happen to have chose the other polyatomic ion to start with, so if you happen to do that and go, okay, I need 3 here, as soon as you get to the silver, you would see obviously it doesn't match. So all you would have to do is take this number and multiply them, and then you would have the right number, and then you would go with 6 and continue on your way. So that's a way, if you happen to choose maybe so the wrong polyatomic ion, you can kind of easily fix it pretty quickly as well. All right, any questions on balancing? Obviously, any equation that you have should be balanced. You should always check it to make sure it is balanced. And just in case it is not, then make sure that you do balance it. All right, so let's talk a little bit about electrolytes. Electrolytes are substances that when they do dissolve in water, they break apart into ions, and they can conduct electricity. And it's really the presence of those ions that help conduct electricity. A non-electrolyte, on the other hand, will not conduct electricity. It will still dissolve, but it will not produce any ions. So that is really the key to producing electricity, is the ions. So you get no ions here, and ions here, you get yes. So if you have a strong electrolyte, it will conduct electricity really well. A weak electrolyte, not so much. And a non-electrolyte will not conduct electricity. So a very common example is they hook a light bulb with some electrodes, they stick it in the solution. And in a non-electrolyte, because there's no ions, it will not go off. In a weak electrolyte, the light bulb will turn on because it's able to conduct electricity, but nowhere near a strong electrolyte. And a strong electrolyte, as you can see, will conduct electricity really, really well here. So what is the difference between those? Let's talk first off about a strong electrolyte. A strong electrolyte will 100% break apart into ions. So when you have a strong electrolyte, there's pretty much nothing left there in terms of the whole units. So for example, sodium chloride solution, when you have a sodium chloride solution, it will 100% break apart into sodium ions and chloride ions. So this is 100% what you have in the solution. You have none of these guys still together. So you have none of the sodium chloride units still together, basically again floating around in that solution, bunch of sodium ions and chloride ions. Again, our light bulb will go off really well because it's loaded with ions, so it'll conduct electricity really, really well and be very bright. Now that's a little bit different than what we see with a weak electrolyte. A weak electrolyte will mainly stay together. But will break apart into a few ions. So because it's still able to produce a few ions, it's able to still conduct electricity, but kind of like the light bulb example we just saw, it will be very, very dim. So it's not going to be able to conduct anywhere near as strong electrolyte. For example, hydrofluoric acid is a weak electrolyte here. Most weak acids or weak bases are as well. It will break apart into H plus and F minus. Unlike the other electrolyte, this guy here is mainly what you have. So you mainly have the whole HF unit still together, but it will produce a little bit of these ions. So basically in the solution, mainly the HF still floated around together, but you will have a little bit of H plus floating around, a little bit of F minus floating around. And again, because of the presence of those ions still there, it's able to still conduct electricity. But like I said, really nowhere near what a strong electrolyte can do. Then obviously a non-electrolyte, as it mentioned, will dissolve in water, but produce no ions. And again, it's that lack of ions that will not allow it to conduct electricity. So for example, if you took sugar and you dissolved it in some water, the sugar obviously will dissolve in the water. But because sugar is really covalently bonded, carbons, hydrogens, and oxygens, there's going to be no ions being produced in this case. So you will have not conducted electricity. So really no electricity conducted. So how do you tell sort of the difference? A couple important things. When we look at a strong electrolyte, pretty much most ionic compounds are strong electrolytes. Strong acids, strong bases are strong electrolytes. We have really a one-way arrow, basically. It's all dumping out to the product side. Nobody's coming back the other way. And that is different than what we see in a weak electrolyte. A weak electrolyte has arrows heading in both directions. It is a reversible reaction. So there's a forward direction and a reverse direction. So what happens in a weak electrolyte is it will break apart into some ions, and those ions will decide to come back together and come back and go back to the left-hand side. Eventually, it will reach equilibrium, which means the rate at which it goes to the products will equal the rate at which it comes back. Basically, what that means is the concentrations of everybody will sort of lock into place at that point. So that's definitely how you can recognize a weak electrolyte. It will have those arrows kind of heading in both directions. It's definitely a weak electrolyte. And obviously, something that's a non-electrolyte will pretty much, if you look at an equation, will have the same thing on both sides and no ions really produced is how you know that. Any questions on that there? Water, right? Pure water is a good or bad conductor of electricity? Pure water is a bad conductor of electricity. Yeah. There's no ions in pure water, right? So safety note is obviously the water that comes out of your faucet is not pure water, yes, and you will electrocute yourself if you blow dry your hair in the shower. But they actually put ions in it to clean in water and stuff. So there's a lot of ions and stuff floating around, which is why you do get electrocuted. But technically speaking, pure water, if you had just H2O by itself, nothing else in there, actually won't conduct electricity really well because there's no ions basically being produced. What's that? Right. So, you know, most water coming out of any pipe, any place, outside, inside, is not pure water. So you will electrocute yourself. Do not do anything dumb to electrocute yourself. Safety note of the day. Yes. All right. But you know, technically speaking, deionized water doesn't have ions in it, but it could still, based on the filtering system, still have some in it and electrocute you, right? So obviously, as I mentioned before, strong electrolytes are typically anything that's ionic for the most part. Any strong acids, which by the way, some strong acids are hydrochloric acid, nitric acid, perchloric acid, sulfuric acid, hydrobromic acid, hydroiodic acid. So those are all some strong acids. Strong bases as well. A lot of strong bases have hydroxide in them. So things like sodium hydroxide, potassium hydroxide, pretty much anybody from group 1 or 2 on the periodic table mostly that have OH in this formula will be probably a strong electrolyte. So any of those things there will pretty much 100% break apart in solution. They'll conduct electricity really well, and you will not have any of the whole units still together. A lot of weak acids, like here, this is acetic acid, basically vinegar. So HF is a weak acid. Acetic acid here, nitrous acid, carbonic acid, sulfurous acid, and so forth. So these are some weak acids or weak electrolytes. They mainly stay together. Weak bases, there are a few, but a common weak base that you come across a lot is ammonia. So ammonia is a weak base as well. So if you have any of these guys, you would mainly expect them to stay together. Again, not really break apart into too many ions. They still will, but again, pretty much going to kind of stay together because of that. And again, we do see our sort of reversible reaction there. And again, those arrows means a forward direction and a reverse direction. And like I said, at some point, they will reach what is known as equilibrium with each other. And that doesn't mean, again, that they have the same amount of each guys on each side. It's really talking about the rate of the forward direction of that reaction will equal the rate of the reverse direction. And like I said, basically what happens in that case is it just really locks everybody into place in terms of where they are, in terms of their concentration at that point. It really doesn't change all that much when they reach equilibrium. It doesn't mean, again, they have equal amounts, but they just kind of stay wherever they are at that point. Now, again, what happens with, say, ions when they do go into water is they do get surrounded by basically water atoms, and that is the process known as hydration. And that's because water is polar, right? So the oxygen side of water is more negative, hydrogen side is more positive. So when we do dissolve something like sodium chloride in there, it is the negative side of water, which is the oxygen, surrounds it. While the chloride ion gets surrounded by the positive hydrogen all the way around. That does really two things. That's pretty much how something dissolves. And it gets surrounded by so many waters that we visually cannot see it anymore. And it looks like it's gone. It's just kind of surrounded by all these waters and it's no longer sort of visible to us. We know it's really still there because, as we did in a couple of experiments, what happens when you start heating these guys? All of the water molecules evaporate off, right? And that allows those ions to come back together and you're left with a solid, like in your evaporating dish in those couple of experiments that you did where you had the water bath, you put it up there, all the water evaporated off, and you were left with like a solid that was left in there. Again, when you started the evaporation process, you really couldn't see the solid, right? It was all sort of in the liquid state, right? Or really a solution. But by evaporating off the water, it allowed this two ions to come back together, like our silver chloride ion, right? Or our tin and oxygen that came together in the other sort of experiment what we did. So there's a table of some strong electrolytes, some non-electrolytes, and again, some weak electrolytes here. And these are good ones to perhaps know or be able to find as you look through it. All right. So let's talk a little bit about solubility. So solubility is the maximum amount of solute that you can dissolve in a given quantity of a solvent at a particular temperature. If something is soluble, it means pretty much everything dissolves. And when we talk about something being soluble, it usually will get the aqueous symbol, which means you kind of make a solution. Everything dissolves into each other. If something is insoluble, it usually will end up with the solid sort of symbol, which means at some point you will make a solid, which is referred to a lot of times as a precipitate, as it says on the next page. Precipitate. Sometimes referred to as a PPT or precipitate. So this type of situation where we do precipitate out some does come with a certain type of reaction. And the type of reactions we're going to talk about here are really one big category of reactions, which are known as double displacement reactions. And double displacement reactions basically have this general formula, AB plus CD. And what makes these guys what they are two ionic compounds. So we have two ionic compounds. And basically what will happen in a double displacement reaction always is the two positive guys will switch partners. So they will switch partners. And we will end up with two new ionic compounds on the right-hand side, like A and D coming together, and C and B coming together here. Now, there really is sort of three reasons why a chemical reaction takes place. The three reasons for a chemical reaction is basically the formation of a solid. So the formation of a solid is one reason why a reaction takes place. The formation of water. And lastly, an electron transfer. Those are basically, if you cut it down to the heart of it, those are really the three reasons why a chemical reaction takes place. There are really the three things that are happening in pretty much all chemical reactions. Either you made a solid, either you made water, or you transferred some electrons. It's basically the three things that happen. Now, for double displacement reactions, they actually take care of the first two. They take care of the formation of a solid. Like, for example, one of these guys makes a solid. They also take care of the formation of water. So maybe one of these guys becomes water in that process. The third reason a reaction takes place is really a different category of reactions, and those are what are referred to as redox reactions. And redox reactions are oxidation and reduction reactions. And what basically happens in those, as we will talk about, is there's some type of electron transfer that occurs. So really, when we talk about reactions, which we're going to talk about for the rest of this chapter here, they really do fall under sort of two different umbrellas: double displacement reactions, which takes care of either you made a solid or you made water, and redox reactions, which means you ultimately transferred electrons, even though it may not appear you did, but you actually did transfer of electrons. So we're going to start with sort of the double displacement route, and more specifically, the precipitation reaction, and how we know if we get a precipitation to occur or not. So let's take a look at that one first. So precipitation reactions are a subcategory of double displacement reactions. So they really do sort of fall underneath that category, which again is our sort of two ionic guys that are going to switch partners. And in this case, one of them makes a solid, which is why it's called a precipitation reaction. So if we look at this reaction here, which is lead to nitrate, which is aqueous, is a solution, added some sodium iodide, which is also a solution, both kind of colorless, by the way. When we put these guys together, we will actually get a solid that forms lead to iodide, which is the yellow solid, and some sodium nitrate. Now, we know this is a double displacement reaction because this is an ionic compound, which is a positive and negative guy. And this is an ionic compound, which is a positive and negative guy, which means basically what happens, as we can see, is the two positive guys switch partners. So the lead ends up with the iodide on the right, and the sodium ends up with the nitrate on the left-hand side. So this is the balanced molecular equation here. But we could actually write another equation that really describes sort of what is happening, say in the beaker or the test tube when you kind of toss it in there. And we could do that by breaking apart anything here that is a strong electrolyte. Anything that's a weak electrolyte will stay together. Anything that is a solid, a liquid, or a gas will stay together. So for example, lead 2 nitrate is a strong electrolyte. It's ionic. In solution, it's not going to stay together because it's a strong electrolyte, and you will get a lead with a positive 2 charge. There are 2 nitrates. You will get 2 of the nitrates with a negative 1 charge. The sodium iodide here, also a strong electrolyte, which means it will break apart as well. And you will get 2 of these sodium ions. And that 2 will also distribute to the guy behind it, 2 of the iodide ions. Now, when we come to the other side here, the lead 2 iodide, which is a solid, that yellow solid, technically will actually go to the bottom. If you centrifuge it out, it will just drop to the bottom. And we do keep it together because it's a solid, because if it didn't stay together, it wouldn't be a solid. So we would not break this guy apart. We would keep it together. And again, like I said, anything that is a solid, anything that's a liquid, a gas, or a weak electrolyte actually will stay together when you're writing this equation. The sodium nitrate here is a strong electrolyte, which will break apart into 2 sodium ions. I'm running out of room, so I'll go right underneath. And also 2 nitrate ions as well. So this equation here that I wrote, which basically breaks apart all the strong electrolytes, this is what is known as the total ionic equation. Or sometimes people call it the complete ionic equation. And since it is an ionic equation, my ions have charges, yes? So you need to write the charges here. When we look at this, this is basically what's describing what's happening in the solution as everybody's floating around. When you get to the total ionic equation, you can look on the left-hand side of the arrow. You could also look on the right-hand side of the arrow, and you'll be able to find ions that look exactly the same. So if we do that in this particular case, on the left-hand side of the arrow, I have 2 nitrates. On the right-hand side of the arrow, I have 2 nitrates. Left-hand side, I have 2 sodiums, and I have 2 sodiums on the right-hand side as well. These ions that are the same, and they look exactly the same on both sides, and if you did it correctly, should be the same number of ions on both sides. These are what are referred to as spectator ions. And if you are a spectator, you are pretty much just watching. And that is pretty much what is happening here. These ions are there simply just to balance out the charge. They're really not participating in the reaction that's taking place. And what we typically do with spectator ions is we cross them out. So we get rid of the nitrate on both sides. We get rid of the sodium on both sides. And this leaves us a third type of equation, which is known as the net ionic equation. And it really tells us what is happening in this reaction. What is really happening is the lead-2 ion from the lead-2 nitrate is going and finding some iodide ions, and they are coming together to make this solid, which again is one of the driving forces for why a reaction takes place, the actual formation of a solid. And this is what is known as the net ionic equation. So basically it tells you pretty much this is exactly what's happening in this reaction, getting rid of all the other guys. They're just there to balance out charge and not really participating. Any questions on those different types of equations? So how do we know, if we will get a solid, if we put two things together or not? There are some rules to help us decide when we are putting things together. Would we expect it to be a solid? Would we expect it to be aqueous and not a solid form? So let's take a look at some of that there. Pretty good, yeah. So these are what are referred to as solubility rules, and solubility rules are what we use. By the way, these are in your notes a little bit further back. I kind of moved them forward a little bit from your notes, so you could find them in a few slides towards the back, I think, of your notes, or towards the middle back. These are guys that are typically soluble. So things are typically soluble. These are guys that would get the aqueous symbol, which means we would not expect any type of solid to form. So basically lithium, sodium, potassium, pretty much anybody from group 1, if you see it in a formula, it's always going to be soluble. There are no exceptions. You pretty much can just lay up the aqueous symbol next to it and move on with your life. Same thing with ammonium. If you see anything that has NH4 in the formula, it's going to be soluble as well. It will get the aqueous symbol. There are no exceptions. Anything that has nitrate or acetate in it will also be soluble. There are no exceptions. So if you see any of these guys in any formulas, they are all going to get the aqueous symbol. Anything that has chloride, iodide, or bromide in the formula will be soluble. But there are a few exceptions, and these are the exceptions. If you had either chloride, bromide, or iodide with silver, mercury 1, that's what that is, and lead 2, then it's going to be an exception, which means instead of it being soluble like it would be here on the left, it then would become insoluble and get a solid. So if you have one of the exceptions, it moves it from being soluble to insoluble. Same thing with sulfate. Anything with sulfate is typically soluble, except if it is sulfate hooked up with anybody on this side. If you have anybody on this side with sulfate, it will become insoluble and will become a solid. Any questions on that there? So if we look at some things that are typically insoluble, so these are guys that are typically insoluble on the right or left, which means they typically will get the solid symbol. Anything with hydroxide will typically be insoluble, except that if it's attached to something in group 1, which basically is the same rule as we just talked about on the other slide, or ammonium, it will make it soluble and aqueous. They are slightly soluble with barium, calcium, and strontium. Most people consider slightly soluble as leaning more towards being insoluble in most cases. In that case, anything with sulfide typically will produce a solid, again, except if it's group 1, which is the same thing we talked about on the other side, and some group 2 guys here like calcium, strontium, and barium. They would then become aqueous. And lastly, carbonates and phosphates are typically insoluble. except once again, if it's hooked up with group 1. So most of the exceptions here is basically the group 1, which tells you it's soluble in everything. So once again, if you see group 1, you're going to know that's going to be soluble, so you don't have to worry about the exceptions here. Any questions on that there? So if we took something like silver nitrate plus some potassium chloride, making a little double displacement of silver chloride plus potassium nitrate here. If we were going to use our solubility rules here to determine, we would start with the silver nitrate, and although I may not see silver on the left-hand side, I do see nitrate on the left-hand side. And what I see in terms of that is nitrates are soluble in everything. Nitrates are soluble in everything, and there's no exception, which tells me that that guy is going to be soluble, so it would get the aqueous symbol next to it. When I look here, I see potassium, which is group 1, which means that's really as far as I need to go. That is going to be soluble in everything. Once again, chloride will be soluble in everything except for silver, lead, or mercury. That brings us to here, which is silver, but we can see chloride, which once again on the previous page, soluble in everything except for silver, lead, and mercury. And this is obviously the exception. So instead of chloride being soluble in this case, it will now become insoluble because it's attached to the silver. And that would be our precipitate that would form here. Once again, here, potassium is soluble in everything. So is nitrate. We could really look at either one there, and that would give us our aqueous symbol. Any questions on that there? All right, so let's take a look at some here. So take a moment here for each of them. Will they be soluble in water or insoluble in water? Look, so really here I see potassium, and that is group 1, which means I don't need to go any further. This is going to be soluble. Would get the aqueous symbol. You could go further and look at hydroxide, where the exception would be hydroxides are insoluble except with group 1, which then this would make it soluble as well. This is bromide, which is soluble in everything except, from our rules, silver, lead, and mercury 1 here. That means that is silver, which makes it an exception. So this would be insoluble in this case and would get the solid symbol next to it. And we would expect a solid to form. Calcium chloride, once again, chloride. These are the 3 exceptions for chloride, and that is not one of them. And that means that this will be soluble. We have lead, but more importantly, we have nitrate, and nitrate is soluble in everything, no exceptions. Which means we would also expect this guy here to be soluble. And lastly here, which wrong way? There we go. Lastly, we have sulfate. And again, if we go back to our table, look at sulfate. Sulfate is soluble in everything except for silver, calcium, strontium, barium, or lead. I believe that last one was lead, right? So that would be the exception. So instead of being soluble like it normally is, it would then be insoluble because it's hooked up with lead, and it would get the solid sort of treatment. Any questions on how to use solubility rules? Yeah. I'm thinking you might have something that would help you. No. You'll have some type of rules. You should be familiar with some of them because it definitely would be helpful, but you would probably have it as given to you. You know how to use it, I suppose. All right, so we kind of did that one. So let's do this one here. Write the equation for the precipitation of potassium carbonate and nickel 2 chloride. So why don't you do the balanced molecular equation, the balanced total ionic equation, and the net ionic equation. So why don't you take a couple minutes and come up with that. So do all 3 that we were just talking about, molecular, total, and net ionic equation here.